Limits at infinity. What happens when you look at the limit of a function as x approaches positive infinity or as x approaches negative infinity? And then what's the behavior of the graph and the function when the limit itself is equal to infinity? Sometimes it can be as x approaches a number, or when x approaches infinity, that the limit of the function may come out to be infinity. So what do you do? Let's look at some techniques today to determine how to examine and then to solve limits at infinity. The definition of this is seen by letting L be a real number. The statement, the limit of f of x as x approaches infinity is equal to L, means that for each epsilon greater than 0, there exists a capital M positive, such that the measurement, hopefully a constant measurement eventually, of the difference between the function f of x and L is said to be always less than some fixed number epsilon. And this is whenever x is greater than capital M. What happens when the limit of the function as x approaches negative infinity is equal to L? What does that mean? For every epsilon positive, there exists a capital N negative, such that the difference of the measurement between f of x and L is less than epsilon whenever x is here less than capital N. Now, what does that mean graphically? I think this is ideally what we're saying, that as x approaches infinity, what happens to the function values or the y values? Back in algebra, we just called that the horizontal asymptote. So here, the definition of the horizontal asymptote, the line y equal to L is the horizontal asymptote if you have the limit at infinity. That is, the limit of f of x as x approaches negative or positive infinity is equal to L. So the limit of a function comes out to be, for us, the horizontal asymptote. Let's see. Let me interject this here. The limits at infinity can also be examined by looking at if it's a ratio. The limit of c over x to the r as x approaches infinity is equal to 0. And then if x is going to negative infinity, then of this particular ratio, x is getting larger. It's downstairs in our denominator. R is a fixed power, so you get 0. Guidelines for finding the limits at plus or minus infinity. Here for a rational function, this is the 3-step definition for the horizontal asymptote to be able to determine whether or not the horizontal asymptote is equal to 0, the horizontal asymptote is equal to the ratio of leading coefficients, or that the horizontal asymptote does not exist. So if the degree of the numerator is less than your degree of the denominator, then the horizontal asymptote, that is the limit, is equal to 0. If the degree of the numerator is equal to your degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. That is, it's just infinity. Infinite limits at infinity, as if we were infinitely finished with limits of infinity. So here the definition of an infinite limit at infinity simply says that what happens to the limit of a function as x approaches infinity when that result itself is equal to infinity. And you could get negative or positive infinity. It just very much depends. Typically, we have the limit equal to infinity, typically, not all the time, is when you want to examine what happens at the vertical asymptote. Sometimes that is the case. Here, as x approaches infinity, you get something a little bit different. So let's look at some problems and see if we can make some sense out of it. So here, find the limit So for the first one, And I'm just going to use just simple techniques to being able to determine the limits. Look at these three problems, A, B, and C. They want you to examine the leading coefficients, that is the degree of the numerator and your degree of the denominator. So the degree here is 2, this degree is 3. If the degree of the numerator is less than your degree of the denominator, then the limit is automatically 0. That is as x approaches infinity. If the degree of the numerator is the same as your degree of your denominator, then the horizontal asymptote, or the limit, is equal to the ratio of the leading coefficients. 1 divided by 1 is 1. If the degree of the numerator is greater than your degree of the denominator, then your limit here is infinity. That is, the limit does not exist. What about this limit here? Well, the limit of this constant 4 is 4. The limit as 3 over x, as x goes infinity, this guy here goes to 0. So you have left 4 plus 0 is just 4. The limit of this term, notice again that the leading coefficient is 2 for the numerator, the leading coefficient for our denominator is 3, but their powers or their degrees are the same. So the limit becomes the ratio of the leading coefficients, 2 divided by 3. Here, when the degree of your numerator is less than your degree of the denominator, the limit is automatically 0. Well, look at this. Here we get infinity because our degree of the numerator is greater than our degree of the denominator. So we get infinity, but here x is going over negative terms. So this becomes negative infinity. Now, let me get more specific. Boy, I tell you, my dad couldn't say these S words either. I get in detail with this problem so you can kind of see what's happening. Here, and I could have done the same thing for all these problems, but I think just doing it the easy way is always better. Say, for example, there's several ways you can find these limits. If you notice that all of them we have an indeterminate form. Like this guy is infinity divided by infinity. So you can use L'Hopital's rule if you want. Use L'Hopital's rule. You can use my method of just the horizontal asymptote. I'm fine with that. So this is the limit as x. Just want to show you a different way. As x goes infinity, we apply L'Hopital. The derivative of the numerator is 2, and our derivative of our denominator is 3. So the limit of a constant is a constant, 2 over 3, right? The same thing here. You have infinity divided by infinity squared, so you can apply L'Hopital's on this one. And so we have the derivative of the numerator is 1, and the derivative of our denominator is 2x. Now, the limit of 1 over 2x, as x gets large, this is 1 over large values continually. So these terms get smaller and smaller. The ratio gets smaller and smaller and goes to 0. Same thing here, infinity over infinity. So we have the limit as x approaches negative infinity. We take the derivative of the top, that gives us 10x divided by 1, right? Now, as x goes to negative infinity, 10 times x goes to also negative infinity. There's another method, and I'll just show you with one of these up here, possibly with the first one. There's another technique that we use, and that is you look at the ratio, if you're looking for the limit, especially here as x goes to infinity, and you divide each term by the biggest term in that relationship. Well, the biggest term here would be x to the third. The biggest term for part B would be x squared. The biggest term here would be x to the second. And so this serves as a way of dividing out. We have the limit as x goes to infinity of x squared over x to the third plus 2 over x to the third all over x to the third divided by x to the third minus 1 over x to the third. Now we simplify. This is the limit as x goes to infinity. Here, this 1 over x cubed as x goes to infinity, this guy goes to 0. 2 over x cubed as x goes to infinity, this term, the 2 over all of this, that goes to 0. And we simplify what we have. This is 1 over x, and this is divided by, this is just 1. The limit as x goes to infinity of 1 over x, and as x goes to infinity, 1 over x goes to 0. Oh boy. So whichever method you use, you come up with the same thing. I use my easy method, just the horizontal asymptote from algebra, and you're done. Now with this guy, now he requires just a little bit more insight because of this radical, right? So here, divide each term by the biggest term here, which is x. This is the biggest term downstairs is the square root of x squared, which is technically x, but doesn't look like it. We have to fix it up. Each term by x. And for the denominator, you need to find something comparable because of that square root, and x is going over negative terms. Here we use x is equal to negative square root of x squared. Since x is negative, right? We know that the absolute value of x is defined as the square root of x squared, right? And so negative, the absolute value of x, is defined as negative the square root of x squared. And that's what we're using for downstairs. X itself is said to be negative, so we just write divide by x in our numerator. So this is the limit as x goes to negative infinity. This becomes x divided by x all over the square root of x squared minus x divided by negative the square root of x squared. This is the limit as x goes to negative infinity. The numerator is 1. This is all over negative times the square root. This becomes x squared minus x divided by x squared. X squared downstairs is inside that radical. We simplify it. This is the limit as x goes to negative infinity. Just put the negative sign up top. This is -1 all over the square root of, this is 1 minus 1 over x. Investigation. Now, as here, as x goes to negative infinity, 1 over x goes to 0. That part goes to 0, so now I have left -1 divided by 1. I don't want to get too close over here. I start to hit up against myself. Yeah, I made it funny. So this is the limit as x goes to negative infinity of -1 over 1, which is just -1. The limit of a constant is a constant. We'll just have -1. I'm going to stop there, and then we'll come back and finish this section by looking at some graphs, okay?